So this is my lecture 8. So in the last 4 classes, we saw how lag lead and lag lead controllers can be designed based on some frequency response specifications such as phase margin, gain crossover frequency, and also a steady state error specification. And we saw that lag lead and lag lead controllers that we have designed are mostly first order or second order. Lag and lead controllers were first order, and lag lead controllers were second order. So that method is applicable for first or second order controller design. But if your system is of higher order, so then that first or second order controller may not be able to give desired performance and robustness. For that, you need a higher order controller sometimes. So that's why another method of controller design we'll discuss, which is also known as a time domain based approach. You can say some because some this some time domain specifications you can meet. Although time domain and frequency domain specifications are correlated to each other, but still here time domain specification you will be able to meet directly. So such a method is known as that is a general controller design method, and it is applicable and using using the controller design method that I will be discussing, that you can use for any higher order system also. The controller method is pole placement based. So pole placement based, pole placement. So anyway, whatever controllers we are designing, ultimately we are placing poles at some desired locations by directly or indirectly, lag, lead, or whatever controllers use. Ultimately, we are doing some sort of pole placement, but here we will be able to see how directly pole placement can be done, can be achieved using an output feedback control. So this is the first I will consider is 1 degree of freedom control. 1 degree of freedom, dynamic output feedback control. Okay, so this is the feedback configuration that I will be using. 1 degree of freedom means why it is called 1 degree of freedom. That also I will be discussing. So this is the feedback diagram. So I am considering, say, output disturbance for the timing, and I am not considering any distance filter or something kind of thing, but you can consider that also. So this scheme is also known as unity output feedback scheme, because here you can see this is a reference input, this is the output, this is disturbance, and this is eta. Eta is your noise, or that is a measurement noise, and D is high frequency signal compared to system bandwidth. System bandwidth means bandwidth of the closed loop system. So here this is your plant and this is your controller. So this controller is called 1 degree of freedom controller, HS, because here the the input is only one input, one independent input is going, that is the error. That's why it is called 1 degree of freedom control. So if there are two independent inputs are going, then it is called 2 degree of freedom control. That also will be seeing. So in control literature, 1 degree of freedom and 2 degree of freedom controls are there. 3 degree of freedom controls are also possible. In that case, 3 degree of freedom is disturbance. Disturbance. If it is a disturbance is also measurable, then you may call it as 3 degree of freedom control. That also we can have, but up to 1 degree of freedom and 2 degree of freedom controllers we will be discussing in detail in this course. But the degree of freedom, as I am saying, in case of controller, in respect of controller, the degree of freedom is the number of independent inputs that is going into the controller. Here the number of independent inputs for the controller HS is only one, that is E, tracking error. Okay, so that's why it is called 1 degree of freedom. So here just I am writing number of not number of well, I'll just write the independent input, the independent input the independent input to the controller is tracking error. This implies, that means one independent input, this implies 1 degree of freedom control. So in case of 1 degree of freedom control, tracking error is the only input. So what is the plant structure? So now I will consider a general plant structure. So this is my plant. Plant is my G. So what is a GS structure? GS structure is like this. We will consider nth order plant. General plant we will be considering Sn plus a n minus 1 s to the power n minus 1 plus up to dot plus a1s plus a naught. This is the denominator polynomial or pole polynomial of the open loop plant of the plant just, and this is your numerator polynomial n minus 1 s to the power n minus 1 plus c n minus 2 s to the power n minus 2 plus up to dot c1s plus c naught. So you can say that is a general plant. Any general strictly proper plant it will present, because this plant, what is the relative degree of this plant? This plant relative order or relative degree is the difference between the number of the difference between the number of poles and zeros. So here poles is n, number of poles is n, and number of zeros are n minus 1. So the relative degree is 1, or you can say the degree of the difference between the degree of the denominator polynomial and numerator polynomial. So here, so this plant is general in this sense that it represents any strictly proper plant. For example, if it is a relative degree 1 plant, then Cn minus 1 not equal to 0. If it is relative degree 2 plant, then Cn minus 1 equal to 0. So and so on. So this is a general plant. Okay, so this is that's why I'm writing. So this is equal to, I'm just denoting this is as, this is definition equal to Cs by As, small cs. This is small c, small cs by As. So Cs is the numerator polynomial, As is the denominator. So this is a general strictly proper plant. So now controller I will choose. So unlike lag lead or lag lead controllers, so that those were only first or second order. So here, of course, higher order lag lead controllers can also be designed, but that is no standard methodology is there for that. So that's why we are considering this one general 1 degree of freedom output feedback control design using pole placement based method. So now, what is your controller? Controller is, so this is my controller. This is my controller. Controller transfer function is CS. Sorry, I have considered HS. So HS equal to, I will consider in this form. So this is mth order controller, s to the power m plus k m minus 1, s to the power m minus 1 plus after dot plus k1 s plus k naught, and in the numerator it will be h m s to the power of m plus h m minus 1 s to the power m minus 1 plus after dot plus h1 s plus h naught plus dot dot dot. So now you can see here I have considered strictly proper plant, but here controller, what is the order here? Relative order is 0. So that's why it is a biproper, general biproper or bicasual, general biproper mth order controller. So plant is always strictly proper in nature, because they have low frequency, and that means they have low frequency. Their behavior is like low pass filter. All physical plants, but the controller is in our hands. So controller can be made by proper, so as to have maximum number of tunable variables. So here, so for an mth order power plant, so how many tunable variables you have, tunable gains you have in the numerator m plus 1, and in the denominator this is m. So 2m plus 1. So if it is a first order controller, then 2m plus 1, that means it is a three control gains will be there. So it is deliberately made by proper, so as to have maximum number of control gains we can have given an order of the of the plant. Sorry, given an order of the controller. So that's why this controller is made by proper. So why just in one point I am writing controller is made by proper. Okay, in the next page I will write note the controller in general is chosen as a biproper one, as a biproper transfer function, so as to have maximum number of tunable parameters. So as more number of tunable gains you have for the same order, of course, without order. So as we will have more number of tunable parameters, you will have more flexibility in your in shaping the response. Okay, so suppose first order controller, if you choose a strictly proper first order controller, then only two tunable variables will be there. Two gains will be there in the numerator, one gain, and the denominator, one gain. But if you consider a biproper first order controller, then you will have three gains: H2S plus, sorry, H1S plus H naught divided by S plus K naught. That means three gains. So this is the reason why I have considered here biproper controller. Now, controller order, choice of controller order. So choice of controller order is also important. So just I am marking. So this is my plant. This is your controller. So now choice of controller order. Choice of controller order. So this is also an important thing. How will we choose? What is the minimal control order given a planned transfer function? What is the minimal control order needed to have complete placement, arbitrary placement of all the closed loop poles? So now, if you have a GS as plant and HS as controller, so what is the closed loop characteristics equation order of the closed loop characteristics polynomial? So the order of closed loop pole polynomial is m plus n. Right, mth order plan controller and nth order, so this means m plus n closed loop poles have to be placed at desired location. So where to place that I will come for it, so that will depend on your experience. So there are some ways, some rules are there that I will let you know. So m plus n closed loop poles you have to place. So how many number of now the number of tunable variables, number of gains of the controller, how many control gains are there? So m plus 1 in the denominator and m in the numerator, so 2m plus 1, 2m plus 1. So this implies 2m. So number of free variables should be at least equal to the number of closed loop poles to be placed. So 2m plus 1 should be greater than equal to m plus n. So this implies m should be greater than equal to n minus 1. This is very important equation. Okay, so this is very important thing. So number of closed loop the order given an nth order, so nth order plan, single input single output, general strictly proper, I should write general strictly proper CISO plan, single input single output plan. So if you have a single input single, this can be extended to single input multi output also, that you will be seeing in your design control system design course. Some examples I will consider there. I will some practical examples I will take there which are single input multiple output ones. So you have to design same approach you will use. So here I unnecessarily I do not want to extend all those things. So m is greater than equal to n. So this implies the minimal control order needed. Minimal control order needed to place all the closed loop poles is n minus 1. So this is very important. If n is the plant order, single input, single output, then for arbitrary pole placement, you need to have n minus 1 order controller. So naturally, using first or second order controller, you will not be able to do arbitrary pole placement. And as arbitrary pole placement, you will not be able to do you may not be able to achieve. So now we will see how this dynamic controller, dynamic output feedback controller can be used for pole placements. Okay, this is the condition for minimal order needed. Now I will consider a second order plan and a first order for a second order plan. Then first order controller will suffice. So we will see how these closed loop poles can be placed, and then we will get a general result. So pole placement for a second order plant. So pole placement for a second order plant. Okay, this I will be discussing. So now the plant that I will consider is your GS. GS is according to that structure. It will be C1S plus C naught divided by your S square plus A1S plus A naught. And what is your HS? HS will be as per this structure. As per this structure, it will be H1S plus H naught divided by S plus K naught. H1S plus H naught divided by S plus K naught. So this is your first order controller will suffice to for arbitrary pole placement of a second order plant. Now what is the so the objective is to find K naught, H naught, and H1 given a closed loop pole polynomial. So let the closed loop pole polynomial. So what is the closed loop pole polynomial order? Closed loop pole polynomial order will be 3. This is your ultimately it will be 1 plus this GS numerator of 1 plus GS. So a numerator of 1 plus GS it will be third order, 2 plus 1 third order. So let the closed loop pole polynomial be desired. So I want the closed loop pole polynomial to be like this: s to the power 3 plus delta 2 s square plus delta 1 s plus, sorry, the bracket is not needed, the polynomial delta 1 s plus delta naught. So this I am defining like this I am defining as simple say this I am defining as small delta s. Small delta s. Okay, so delta s is your closed loop pole polynomial. So now the closed loop, what is the closed loop characteristic equation for this plant controller pair? The characteristic equation, closed loop, I know the characteristic equation means there is closed loop. The characteristic equation, characteristics equation is 1 plus GSHS 1 plus GSHS equal to 0. So if you simplify it now, what will be 1 plus GSHS? It will be S plus 1 plus GSHS equal to what? You can also write 1 plus GSHS a polynomial as like this. 1 plus, this is your plant is CS by AS and your controller is HS by KS. Have I defined like that, HS by KS? Well, so this I am defining as small hs by ks. Okay, this numerator polynomial is hs and denominator polynomial is ks. So throughout this chapter, I'll consider these notations. This is equal to 0. So this implies ASKS plus CS HS equal to 0. So this is now AS is here what? AS is S square plus A1S plus A naught. So AS is here S square plus A1S plus A naught. What is your KS? S plus K naught. What is your CS? CS is your C1 again. I'm writing this bracket, but this bracket is not needed. This is C1S plus C naught. So this is your C1S plus C naught. And what is your HS? HS is your H1S plus H naught. This should be equal to 0. So this if you simplify, then it will be coming out to be like this: S cube plus K naught plus A1, please check it, plus H1 C1 into S square plus A naught plus K naught A1 plus H naught C1 plus H1 C naught into S plus K naught plus K naught plus K naught into K naught into A naught plus H naught into C naught. This is equal to 0. So now comparing 1 and 2. So if you compare 1 and 2, then what will you get? So comparing the coefficient. So this is your closed loop characteristics equation, and what is your closed loop desired closed loop characteristic equation? This is your S cube plus this one delta 2 S square plus delta 1 S plus delta naught. So if you compare every coefficient, then what will you get? Every coefficient, if you compare, then the comparing 1 and 2, every coefficient that I am not writing, coefficient of s to the power cube, s to the power square, s to the power 1 and s to the power 0, then what will you get? Because this equation and this equation, that means this is actually is what? This should be actually equal to this actually equal to delta. This equation is actually delta s. So that means those if you compare 1 and 2, the coefficient of s to the power I equal to 0 to I equal to 0 to 3, then what will you get? Then you will get this one k naught plus, sorry, k naught a naught plus h naught c naught. This is equal to, you just see, this coefficient should be equal to this delta naught. So that means this should be equal to delta naught, and similarly this coefficient a naught, this should be equal to delta 1 and this should be equal to delta 2. So a naught, plus k naught a1 plus h naught c1 plus h1 c naught, this should be equal to delta 1. Again k naught plus a1 plus h1 c1, this should be equal to delta 2. Now if you represent, and also 1 is equal to 1, another case we are getting 1 is equal to 1 by taking the last and the coefficient of s to the power cube. So then what kind of equation we are getting? Suppose so this will imply I want to write this kind of equation. What is the coefficient of denominator polynomial k naught 1? So k naught 1. What is the coefficient of numerator polynomial? h naught h1. So h naught h1. This should be equal to what I want. Here I want delta naught. What is the coefficient of delta s? Delta 1, delta 2 and 1. So now if you, so this is your suppose W, and this is your delta bar, say. So then ultimately what you are getting, what will be this matrix? So if you see, so first element will be, if you see the first equation, this into this should be equal to this first equation, a naught into k naught plus h naught plus this is 0, and then it should be c naught, and this should be 0. And then from the second equation, what you will get? This should be 1. Sorry, cannot coefficient is a1. This should be a1. This should be a1, and then one coefficient is a0. Then what is H0 coefficient? C1. And then what is H1 coefficient? C0 should be equal to delta 1. And what is third one? K0. K0 is what? K0 coefficient is 1. And this is your a naught, then a1 into 1, so a1, and this is your h0, and this is your c1. This should be this. And then what is the last one? Last one is 0, and this is 1, this is 0 0. Yes. So that means peculiar a particular structure of matrix we are getting. So suppose this is your S. So you can see. So it is so these matrices are shifting like this. So you see it is shifting. These are shifting. These are shifting. And shifting like this. So this S is known as a Silhouette matrix. This equation will imply S into W. This is equal to delta bar. This is known as Silhouette matrix equation. So this and this is known as Silhouette matrix. This Sylvester matrix has this kind of property. It will shift like this. And so first row A0, A1, A2, then it will shift on one row until this is complete. So this is one has come. Then again another row, another column, C0, C1, 0, 0. Then again this shifting is happening. So this A Sylvester matrix has an important property. Now the important property is S is invertible if CS and AS are mutually prime, okay, or if CS and AS are co-prime, that means if CS and AS does not have any common factor, then it can be proved. It was in linear algebra. I do not know whether you have studied or not. In Hoffman and Kunz book, all these things are there. So in linear algebra course, it is there. The Sylvester matrix is invertible, or in advanced contour theory also it is proved that this kind of Sylvester matrix equation is invertible if this CS by AS is co-prime. So it can be proved. There is no this is a standard result in higher linear algebra. So you can see this dimension is 4 cross 4, and this dimension is 4 cross 1, and this dimension is again 4 cross 1. So this is important. This is your Sylvester matrix equation, and it is invertible. So this implies, this will imply what? You can easily determine what is the controller parameter. So this implies W is equal to S inverse into delta bar. So this is the very important. This is the controller parameter. So this is a controller parameter vector. So controller parameter vector is used to obtain the controller parameter vector. Because W is the controller parameter vector. So this S and delta bar are given. In fact, delta bar you have chosen on your own. How to choose that I will come. So that is a difficult task. So if that is ready with you, then you can easily determine the controller parameters using Sylvester matrix equation. So in this way, you can even this method can be generalized to any generalized to any order system. For example, if you consider an nth order controller, nth order plant, and mth order controller, nth order plant, for nth order plant, the controller order will be n minus 1, So if you consider that and if you follow this approach, then the general result can be written like this. The for general case. So general case means here m equal to control. General case means what? General case means plant order m, sorry, n, plant order n, and the controller order m equal to what? N minus 1. So if you consider this one, then w will be here. W will be like this. You can easily in fact see what will the structure. So you can see that here what is structure? A0, A1, then A1, 1. So how it is followed? So if you see this A0, A1, then 1. So if you have an nth order plant, then it should be, and the denominator polynomial is s to the power n plus a n minus 1, s to the power n minus 1. So it will start from A0, A1, A2 up to a n minus 1, then 1, then 0 0 0 0. And what will be the size? Size should be, here is 4 cross 4. Here is 4 cross 4. Why? How it is 4 cross 4? Because the closed loop pole polynomial was fourth order. Closed loop pole polynomial was third order. Closed loop pole polynomial was third order, but the here the controller. So here it is, the order is order was 2n cross 2n. So here order is 2n cross 2n because n equal to 2. So here order will be general order, general size. It is size, not order. This size is 2n cross 2n. So this will be your first column. Then second column will be 0, a0, a1 up to dot 0. This is your an minus 1, an minus 1, then 1, then 0 after dot 0. So in this way it will continue 0 0 0. So 0 after dot. So then a0, a1 after dot after dot an minus 1, then 1. So unless until it is 1, it will continue like this. Then once this the column involving AIs are over, then your CIs column will start. Again C0, C1 up to dot Cn minus 1, then 0 0 up to dot 0. So in this way, then 0 C0 up to dot Cn minus 2, Cn minus 1, 0 up to dot 0. So in this way it will continue till 2n minus 1 column is over. 0 0 0. So I have written C0, C1, C2 after dot, this is 0. So in this way it will continue, and you can see again this kind of shifting will occur. Okay, so this is general Sylvester matrix equation. This is general Sylvester matrix equation. Sylvester matrix is for general system, general controller design. So what will be your W now? W will be, W is what? W contains the controller parameters. So what are the controller now coefficient? controller coefficient. So there it started from k0 to 1 and h0 to a1. So here it will start from k0, k1, k2 up to dot 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 kn minus 1, and then it will start kn minus 1 was what? Kn minus 1 is equal to 1, of course. You see, cannot k1 after that, so m equal to n minus 1 here, so kn minus 2 and then kn minus 1 coefficient is 1. So here better to write kn minus 2 and then 1, and then after that it will be h0, h1 up to dot 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 h of n minus 1. So this is your 4n cross 1, 4n cross 1, sorry, it will be 2n cross 1, it will be 2n cross 1, and your delta bar will be what? Delta bar will be delta naught delta 1 up to dot 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 delta of. So what is the controller? So in n minus 1th order controller and nth order plant. So the closed loop pole polynomial will be 2n minus 1th order. So this will be 2n minus 2 and this will be 1. This delta of 2n minus 1. Delta of 2n minus 1 is 1. That is monic polynomial. So this is 1. So it will be like this. This is 2n cross 1. Okay, so in this way, any general order controller you can design, any general plan pole placement you can make. Now, what are the transfer functions? What are the important transfer functions that we have to we have to bother about here? So the three important transfer functions we have to bother about: y by r. This is your response. Response will depend on y by r transfer function, and disturbance attenuation, y by d transfer function, y by eta transfer function, and overall u by r transfer function. U by R transfer function will take care of your control input. So your control input also should be within limit. Otherwise, actuator saturation and rate saturation, all those things will happen. So different transfer function in 1 degree of freedom control, and from that perspective, we'll show the disadvantage, what is the problem, what is the limitation of 1D of control, and then we'll switch to 2D of control. So different functions in 1D of control. What are the different transfer function? One is R to Y. So R to Y transfer function is what? R to Y transfer function is Y by R. I am writing in small letter, although I should not write. So this you can easily see. It is GH by 1 plus GH. So GH by 1 plus GH. So it is GH by 1 plus GH. So if you see G is again C by A, H is small h by K. So if you do it, so you will get that CH divided by delta. So delta is where delta is your AK plus CH. CS H's divided by delta S. I am not writing all those S, but actually it will be CS H's divided by delta S. Similarly to d2y. What is d2y transfer function? Disturbance to output. So y by d transfer function will be, you can write it is 1 by 1 plus gh. So this will be equal to ak divided by delta, asks divided by delta s. So delta s is asks plus cshs. And then third is eta to y transfer function. That means your noise, how much noise amplification will be there. So that will depend on this transfer function. So y by eta transfer function is gh divided by 1 plus gh. It is same as r to y. That means but the difference is R is a low frequency signal, but eta is a high frequency signal. So this is equal to CH by delta. You can easily see, and then finally your R to U control effort. So R to U transfer function, R to U, that means U by R transfer function will be your H by, you can easily see H by 1 plus GH. Please verify this one. U by R transfer function, U by R transfer function is H by 1 plus GH. So this will be equal to your AH by delta, ASHS divided by delta S. So now one thing, so what is the limitation? Now you will see the limitation. So what you are placing your, so delta S is in your hand. You can place as you want. But when you are placing delta S, you do not know ultimately what will be the controller parameters. Controller's parameters you will get from Sylvester matrix equation. So HS polynomial, the coefficient of HS polynomial you do not know where they will be. So if the roots of the HS, that means controller pole polynomial, sorry, controller zero polynomial, if the roots of the controller zero polynomial are near to the imaginary axis, then you will see high peak in the output due to the step reference input. So that means yeah, so this is the disadvantage of your 1 degree of freedom control. Similarly, you also do not know where in pole placement delta you are placing, but you do not know where the controller poles will get placed. Controller get, once delta you are placing means controller pole and zero pole will automatically get placed. So you do not know. Because if again the poles of the case are close to imaginary axis, then again amplification in disturbance to output, disturbance attenuation property will be poor. Similarly, noise attenuation property also may be poor if your HS roots of the HS are near origin. So also that control effort will be high if your roots of the HS are near origin. So in summary, so this is the limitation of 1 degree of freedom control. Uh, this limitation has to be avoided because delta S it is in your hand. You will choose delta S as you want, but you do not know where, because of to have that delta S, what will be the HS and Ks, and HS Ks, if the roots are the near to imaginary axis, then your performance ultimately will be poor, even though you have placed the poles at desired locations. So the limitations. So limitations of 1DF control. So limitations of 1DF control. So I have already said, just I will write what is the limitation. So once delta S is chosen, once delta S is fixed, once delta S is chosen, okay, once delta S is chosen, the polynomial HS and Ks, the controller pool, the controller the controller polynomial, okay, and the controller, this is your zero polynomial and this is pole polynomial. Controller polynomials get fixed if this if the roots are if the roots of this polynomials are close to imaginary axis, close to j omega axis, then the following may occur. The following occurs. What? One, roots of h's close to j omega axis causes peak overshoot in output in yt and poor peak overshoot in yt. So more control effort, and so causes one, A, more peak overshoot in yp, B, more control effort, and C, poor noise attenuation. That you can easily see. You just see if so hs is appearing where y by r, and then u by r by u by r and eta y by eta. So that's why these three problems will occur. High peak overshoot, high peak overshoot in yt, more control effort, and poor noise attenuation. This is one, and roots of ks close to j omega axis, what it will cause? Poor disturbance attenuation, because poor disturbance attenuation may cause peak in disturbance response. Okay, peak in disturbance response. Ultimately, that means if it is very close to j omega axis, even particularly if they are in the right half plane, right half plane 0, then it will be a problem. Right half plane root. So that peak overshoot will peaky disturbance attenuation response, or this peaky output, you will peak in your YT means tracking response, then peak in the control effort. So this will occur because of the roots of the HS in undesired position, that means close to imaginary axis. Okay, so also if the control gains HS and KS are high, then control effort also will increase. So many things will be there. The main limitation is this one. So this limitation is very important. So these roots of HS will cause a lot of problem. So now as I said, how to choose the desired closed loop pole polynomial. So some ad hoc method. No, I will not say ad hoc. So so based on my own experience, I will just share you choice of desired closed loop pole polynomial. So how will you choose? So here, based on so two performance specification based on so the method is first choose dominant poles based on peak overshoot and settling time specifications. Even phase margins based on phase margin specification also you can choose, because phase margin is close to is directly related to peak overshoot. Similarly, settling time or rise time is related to your gain cost or frequency. So here frequency response specification also can be met. But this time response specification can directly be met. So because your based on peak overshoot peak overshoot specification, you will get zeta, and based on settling time you will get omega. So zeta and omega n. So from zeta omega n is known and zeta is known. So zeta and omega n separately you can get. So once zeta and omega n separately you can get the dominant pole pair. You can get. First choose the dominant pole pair based on it. So dominant pole pair is what? Minus zeta omega n plus minus root omega n into root under 1 minus zeta square. So what is your zeta? So peak overshoot is equal to e to the power, as you know, zeta pi by root under 1 minus zeta square. And settling time ts. Settling time ts is what? So settling time ts. So settling time ts is equal to 4 by zeta omega n. So from these two relation you will get, then from here obtain zeta and omega n. So once zeta and omega n you get, then you plug this zeta and omega n to obtain this dominant pole location. So this is dominant pole location. Okay. So some, but the problem is there. Problem is the dominant pole based approach. Okay, it is fine. But here when I am choosing this dominant pole, so here I am neglecting what? This is neglecting overshoot, additional overshoot due to the roots of h's. So that I am not taking into consideration. So if you so if you want to consider, as you, so when we are choosing this one, we are assuming that there will be negligible overshoot due to the choice of h's, but that is actually you cannot avoid. So but anyway, this pole pair, this dominant pole pair can be an initial case to choose from the closed loop pole. So this is about dominant pole, and choose the non-dominant pole. The non-dominant pole, the non-dominant pole can be chosen 5 to 6 times. Chosen 5 to can be chosen 5 to 6 times away from j omega axis. 5 to 6 times I am away from minus zeta omega n in the left half plane. Okay. So this is the one way to choose your closed loop polynomial so as to meet 5 to 6 times away, or you can vary. You can make more than that so as to meet some other specification if there is any. So so remember that these two poles will take care of this performance, the settling time, rise time, and all these things. And additional poles you can choose so as to meet your peak overshoot sorry, peak, so, yeah, what's called the control effort magnitude, and disturbance and noise reaction attenuation property. All these things we have to post check now. What is the loop behavior? As I said, so loop behavior, at least after designing your controller, you must post check whether the loop behavior, the desired loop behavior, it is satisfying or not, and accordingly you should change your desired closed loop pole polynomial. It is an iterative process, but the initial guess of how to choose the controller pole, the closed loop pole polynomial that I have given. So the above can be chosen as an the above can be the above can be considered as a starting phase of for choice of closed loop polynomial. So ultimate choice you have to make some iterations you have to make so as to meet some other specifications, as I said. Okay, so this much is for today. So next week, so in the next class, I will consider. I will try to avoid the limitations induced by this HS using a 2 degree of freedom controller at least. So we'll see that reference input to output response and your reference input to that control effort response in case of 2 degree of freedom control will be independent of HS. So that's why that problem can be eliminated using 2 degree of freedom control. Okay. So just I will see once again if I have done minor mistake. This white 2n cross 1, so n is the white 2n cross 2n because n is the plant order and n minus 1 is the controller order, so it will be 2n minus 1. But another 1 equal to 1, that equation I have brought, so that's why it is 2n minus 1 plus 1, that's why it is 2n cross 2n. So this is CH, this is AK by delta, CH by delta, and this is AH by delta. Yes. So if minor mistake is there, typo is there, I will let you know later. Okay. Thank you.